Alright, let's start our discussion of ionic radiuses. We've already talked about atomic radiuses, but let's look at the effects of adding or subtracting an electron. Let's start with the glaringly obvious statement that cations will have a smaller radii than their comparative neutral atom. In other words, lithium will be smaller, lithium ion will be smaller than lithium. Sodium will be smaller than, the sodium ion will be smaller than sodium. The calcium ion will be smaller than the neutral calcium atom. So forth and so on. Now let's state the equally obvious statement that anions, where you've added an electron, will have larger radii than their neutral atom. I mean, I am correct in saying this is obvious. If you add an electron, then that electron has to go out farther than the neutral atom. When you remove an electron, you're usually removing the last on, so you're not changing your nucleus at all. You're not changing the tractor beam strength at all, so it's going to be smaller. So cations smaller, anions larger. Now we get to put on the thinking caps. Which of the species listed below has the largest radius? Okay, first of all, let's locate all these guys on the periodic chart. We have lithium, oxygen, chlorine, fluorine, sulfur. We want to know which has the largest radius. Well, we know that size increases dramatically as you go down. So I'm not going to even bother looking at those. So it comes down to whether I think a neutral sulfur is larger or smaller than a chloride ion. If we consider the neutral sulfur and the neutral chloride very close together, and the neutral chlorine very close together, then we would say that the chloride ion is going to be a wee bit larger because we added that extra electron. Let's take a look at a series of electron configurations for some ions. Let's start with phosphide. Phosphorus has the electron configuration 3p3. To make it into the phosphide ion, I add 3 electrons, and that makes the electron configuration 3s2, 3p6, which is the same electron configuration as argon. Let's take a look at sulfur. The sulfide ion. The sulfide ion, sulfur, has an electron configuration of neon, 3s2, 3p4. If I add 2 electrons to it to make it into the sulfide ion, it has an electron configuration of neon, 3s2, 3p6. And you're saying, yeah, it's obeying the octet rule. So when they obey the octet rule, phosphide and argon have the same electron configuration. But wait, there's more! If we wrote the electron configuration for the chloride ion, we'd discover that it too has an electron configuration that is the same as that as argon. But we can keep going. There's even more. This is better than anything you've ever seen made on TV. We could take a look at potassium. Potassium is argon 4s1. But when it forms an ion, it loses an electron and also has an electron configuration that's the same as argon. Ooh! Let's take a look at calcium. We take a look at calcium, argon 4s2, it forms an ion by losing 2 electrons. And that makes it the same electron configuration as argon. So, that means that the phosphide ion, the sulfide ion, the chloride ion, argon, the potassium ion, and the calcium ion all have the exact same electron configuration. That means that they are what we refer to as isoelectric. And isoelectric means that atoms and ions have the same electron configuration. We refer to these guys as an isoelectric series. Atoms and ions with the same electron configuration. So all these atoms and ions have the exact same number of electrons. That can lead us to a pretty startling conclusion when it comes to some periodic properties. Mainly the periodic property of ionic radius. If we look at this series here, all the ions and atoms in this series have the same number of electrons. So the only thing that is going to affect their atomic radius, or their ionic radius, is their number of protons in their nucleus. Because they all have the same electronic configuration, they all have the same negative resistive force. The only thing that's different about them is the pull of the nucleus due to the number of protons. What happens to the number of protons in this isoelectric series? We go from 15 protons, 16 protons, 17 protons, 18, 19, and 20. So as we go up in atomic number, the pull of our nucleus is going to get stronger because each one of those has the same resistive force because they have the same electron configuration. However, the pull of the nucleus increases with increasing atomic number. Because that Z effective increases with increasing atomic number, we can assume that the ionic radius will get smaller as we increase our atomic number because the pull of the nucleus is getting larger. And this fact that atomic radius decreases with increasing atomic number lets us do some very quick comparisons between atoms. For example, which of the following lists has the species of increase? Whoa, I can't talk. Read the question. All right, let's take them one at a time. Which of the following lists has the species increasing in radius? Well, we've got krypton, and that's not even shown in our figure here. It's down here. And then we have argon. Well, already we've got a no-no with that one. Atomic radius increases as you move down a group. So krypton would be larger than argon. So we can get rid of A already as a correct answer. Next, let's go to another one that's going to be easy to get rid of. Let's go to C. C is your halogens. Fluoride, chloride, bromide, iodide. Those are your group 7A elements. And once again, down a group, radius increases. So iodide would be larger than fluoride. So these guys are actually in the reverse order. Increasing radius would actually go that way. So these guys are in order of decreasing radius, so we can cross them out. Now we can begin to work through our way through some others. Let's go to E next. We have chlorine and sulfur and phosphorus. And then we have aluminum 3+. So we have aluminum 3+, we have chlorine, we have sulfide, and we have phosphorus. All right, quick observation. Phosphide, sulfide, and chloride all have the exact same electron configuration as argon. Right? Phosphorus gaining 3 electrons, 1, 2, 3. Sulfur gaining 2 electrons, 1, 2. Chlorine gaining 1 electrons, 1. So these guys are isoelectric to each other. And we said elements that are isoelectric to each other decrease in radius with increasing atomic number. So our largest radius for those guys would be our phosphorus, fewest protons. Chlorine has the most protons, so it would actually be the smallest. So far, so good. This part matches. Now we run into a problem with aluminum. Aluminum doesn't want to play with the others. Aluminum plus 3 means we've taken away 3 electrons. So 1, 2, 3, aluminum is going to look like neon. Is neon smaller or larger than argon? Before we even factor into a different number of protons, neon we know is smaller than argon. Not only that, but we have fewer electrons in aluminum plus 3. Then we have 10 electrons in aluminum plus 3. These guys here, they all have 18 electrons, like argon. So we have more electrons being pulled by fewer protons than in aluminum, where we have fewer electrons being pulled by a surplus of protons. So aluminum is actually going to be much smaller than the chlorine. So we're not in the correct order there. So we have to cross out E. And my crossing out's gotten kind of messy here. All right, now let's look at our lithium, beryllium, boron. Boron minus 3 electrons, 1, 2, 3, means it would have the same electron configuration as helium. Beryllium minus 2 electrons would have the same electron configuration as helium, and so would lithium. So we have an isoelectric series again. And we said that isoelectric series gets smaller with increasing atomic number. So our atomic radius would go that way for our isoelectric series. This would actually be our smallest. Therefore, we're in the reverse order. Those are in the reverse order of what they're looking for. So that leaves us these. These last little hope for humanity here. Fluoride, oxygen, D here. Let's take them 2 at a time here. Well, let's take them 3 at a time. Notice that fluorine, fluoride, oxide, and nitride are all isoelectric with neon. We said that atomic radius decreases with increasing atomic number. So its atomic radius is going to be larger that direction. So fluoride's going to be the smallest, oxygen, nitride. So hey, those guys are in the right order. Now it's just a matter of phosphide. Well, phosphide's right below nitrogen, and it's down 1. And as we go down, we increase in size. So boom, D is our correct answer in the right order.